Hello everyone, in this video I am going to show visualization of polarization of waves. In textbook we find two typical examples. One is a rope tied to one end and it is given to and fro motion from the other end. The second one is electromagnetic waves. So in this discussion I'll be using the analogy of rope whenever I'm talking. So this is particularly relevant to transverse waves. When we talk of this observation, it is important to set from where we are observing. So all the visualizations which I am showing is the observation is looking into the source, that is the wave is coming towards us or the light is coming towards us and we are observing it. In case of electromagnetic wave, it is either electric field or magnetic field which is relevant quantity of discussion. So what is polarization of wave? We have to look at the shape of the vector, and as a function of time it repeats over each time period. So that shape is what we call as polarization. So if the shape does not repeat, we call it unpolarized light, and if the shape repeats after every time period, then there are three special cases: linear polarization, circular polarization and elliptical polarization. And for linear polarization, two more special cases, that is horizontal polarization and vertical polarization. Most of the time when we talk of electromagnetic waves or plane waves, we generally refer to horizontal or vertical linear polarization. And when it comes to optics particularly, we encounter circular and elliptical polarization. And for both we can have right as well as left, that is right circularly polarized light and left circularly polarized light, or elliptically polarized light right and left elliptically polarized light. Let us see them in the visualization. Now let's visualize those waves in this window. Find our wave. We have wavelength and speed. Let us give some numbers. Let's call it 3 meters and speed as 15 meter per second. And here we can select the special types of polarization. Let us say linear, and we create the wave. And on the right here we get the properties of the wave. So given lambda is 3 meter and speed is 15 meter per second, frequency is phi, angular frequency and wave number. So though these quantities are not relevant for today's discussion, anyway they are there for completeness. Let's look at the axis system. The axis going into the monitor is a z-axis, positive z-axis, and from left to right it is x, and from bottom to top it is y-axis. So we have presently a linearly polarized light and it is horizontal. That means the oscillations occur in the x direction. So what do I mean? Let us first have a look at the wave, and over here on the right we see the time, the running time. So this is the usual wave which we talk. So the wave is propagating into the monitor and it is referred to as horizontal. Let's look at the vector in the horizontal. That will be more easily visible. Each line can be considered as, let's say if this is the light, the strength of the electric or magnetic field, or if it's a rope, the shape of the rope will be like this. So each line which we are seeing is a vector, and that changes as a function of time. Let's look at it. At any point the length of the line increases and decreases. So to make it clear, I have one more graph here which I call it as polarization vector. So one of these lines, that is at z equal to 0, we'll be observing that line. So in textbooks we find both representations. One is the actual wave representation in 3 dimension x, y, z, and generally it is given as in 2 dimensions because it's only a plane wave, so it is given as 2-dimensional graph. And some books give as a 3-dimensional, as you are seeing it here. The polarization is another graph which is actually one of the lines will be shown. Let's see what do I mean. So Ex and Ey. So Ex on the x-axis, Ey on the y-axis. So we can see the vector changes only in the x direction. So in textbooks we find one of these frames. Here I am animating it, so it is oscillating along this line. What happens to vertical? Let us see. This is the actual wave, and you can see the vector is oscillating in the vertical direction. You can imagine it to be the strength of the electric field or the magnetic field, which is function of time. Ex and Ey. So there is no Ex component, there is only Ey component. Next, let us see a circularly polarized light. So as the name goes, circular, the tip of the vector would draw a circle. So the right hand graph is more useful because it conveys the message in a compact and easy form, whereas the left side graph is a three-dimensional actual view. So let us see how does it look. So as it propagates, here it is more easy to imagine it as a rope, and the hand which is holding the one end is going in a circle. It would create this shape of the rope, or this is the strength of the electric field at each point on this line, on this axis. And you can see the arrow goes in a circle. Let's decrease the speed. And you can see the arrow goes in anti-clockwise direction. So that is how two kinds of special circular polarization come into picture, right and left. Also, the circular polarization can have different sizes. For example, this is smaller. It is if a hand is holding the one end, then hand has to move further away. And if it's electric field, it is the strength of the electric field is more if the size of the circle is more. So this circle in Ex Ey, this circle represents that it is circularly polarized light, and as a function of time, the length of the arrow remains constant. Unlike in linear horizontal and linear vertical, the length of the arrow changes as a function of time. Here, most important to remember is the length of the arrow does not change. That is, the strength of the vector does not change. Now let us look at the elliptically polarized light. So again, it looks like an ellipse, and ellipse, there are different kinds of ellipse. One could be aligned to the x-axis or y-axis as it is now. So the tip of the vector rotates and its strength also changes as a function of time, whereas the actual wave itself can be seen in 3 dimension on the left side. Now, ellipse is a more general case from which circular as well as linear can be derived, which I'll show in the next video. But for now, let us look at different types of elliptical polarization. Let's change the shape. Now the ellipse makes an angle with the vertical y-axis. The rotation is anti-clockwise. Let's change it further. The major axis is along the y-axis. Now the circle is more thin and it's making an acute angle with the x-axis. Let's change it further. Now you can see the sense of rotation has changed. It is anti-clockwise. Now this is the linear polarization. Now this is linear polarization can be general. We have seen only two special cases, linear horizontal and vertical, but it can make any angle. This vector, which is oscillating as a function of time, can make any angle with the x-axis or y-axis. Let us see that now. This one, for example. Now this is a more general case of a linearly polarized wave. You can see the wave makes an angle on the left side, and that is represented in the polarization vector. Much more, the angle is much more. Let's say last case of circularly polarized light, where it is rotating anti-clockwise. Almost circle. Let's see this. See, the sense of rotation is anti-clockwise compared to the first circular polarized light which I have shown. It was clockwise. So that's all. To summarize, what you have seen is when the tip of the vector rotates, either it can get a shape or it can be random. So what we have specifically seen is when the tip of the vector produces a shape, we call it polarized. The special cases of linear, circular and elliptical. And in the linearly polarized light, it can either do horizontal or vertical oscillation, very special cases. And when it comes to circular and elliptical, either it can go, the arrow can rotate, that is a vector can rotate clockwise or anti-clockwise. Thank you for watching this video.